as I said, SQL select returns a list. So you will get duplicates. Right? So in the example of Harry Potter, for example, you probably would get lots and lots of copies of the same thing. Right? Because the library will have lots of copies of Harry Potter books, each Harry Potter book. Right? If we want a set as opposed to a list, we use select distinct. Okay? Distinct makes unique. Yeah, so select author from book title, where title, like Harry Potter, would certainly produce lots of instances of J.K. Rowling, right? Because she's written lots of books about Harry Potter. Whereas if I had select distinct author, she'll only appear once. If I want to know all of the authors who have books in the library, I leave out the where part of it. So I'm selecting all authors from the library, but just the distinct ones of them. Another different type of wildcard is a star. Okay, so in this case it selects all the columns. On its own, like that, well, it just returns the entire table. Right? But you might select all the columns where some particular condition is true. You know, like you might want to find all the columns where the book has been on loan for greater than a year, and then you're just going to delete those items from the thing, for example. So there might be reasons for doing the wildcard in that form. I think now. Okay, so we have 10 minutes break at this point. In fact, we'll make it 12 minutes, because what you're interested in is the data from multiple tables. We talked about different types of joins. We looked at Boolean at the algebra, relational algebra. When we're doing it in SQL, we can do it using the cross join or product, as we did in relational algebra. You can do it explicitly using this cross-join operator here. So that's basically saying do a product of these two tables. Or if you just list the tables, it will automatically do a cross-join on them. Right? So what does a cross-join between book title and book copy look like? Well, for each individual item in the first table, we put a copy of each thing in the second table, and there's going to be a lot more rows in this table than this. Right? So notice here, these three columns here, these are the book copy columns. They're all the same at this stage, because so far we're listing the books from the first one. For each book in the first one, we need a copy of each line from that other table. Okay, so it's going to go on and on and on. Perhaps not so useful. More useful is the inner join. Right? So again, we've got the explicit syntax here. So rather than a cross join, we do an inner join. And we need to say on what thing we're going to do the join. Right? So it's the table name dot column name equals table2 name dot column name. Or we can do it implicitly by using a where clause, right? So we're selecting all of the items from book title and book copy where the thing in the first column is equal to the thing in the second column. Okay, so they achieve the same thing. And you'll see that they match, right? So for each line in this table, you should have matching things. We can also have natural join, again, as an explicit command, or we can do it implicitly. So again, just doing commas between the tables that we want to look at with this keyword using. Okay? So in this case, we've only got the ISBN once in the resulting table. Okay? And it's shared between the two original tables, and it doesn't have a qualifier on it, unlike everything else, right? Because it's indicating that it's the shared thing between the two tables. Okay, so we've looked at simple select statements. We've looked at ways of joining tables. Now let's look at some examples of queries. So typically what we'll do is first of all connect tables using either an inner join or a natural join, rarely a cross join, and then project out the desired columns that we want as a new table. So for example here, we're saying I want the names and authors and Dewey ID where the ISBN is shared between the two tables. Here's the same thing using alias names, and all it does is putting in a shorthand for these tables, right? So I'm saying book title is going to be referred to by BT, book copy is going to be referred to by BC, and it just makes this line here a lot briefer and perhaps easier to read, right? If you've got a very complex where clause where you're needing to make a lot of references to particular columns from different tables, it almost certainly will make life simpler if you use this alias name notation. Okay. You can be explicit using the as keyword, or you can be implicit, just leaving it out entirely. Okay, so essentially what's happened here is that SQL, when it was originally defined, was really verbose and had lots of ways of being very explicit about everything. And as it became more and more popular, the programmers who used it got sick of typing this all out and said, this is redundant, we don't need it, let's get rid of it. But for the sake of backward compatibility, all of these things are still available, right? So I, in general, would recommend going with the more simplified form, but you will see it sometimes like this. Okay, so we can also store the result. Okay, so here, this query basically will give you a list, right? Because that's what you get from it. But the list effectively represents a table in itself, right? And so we can call it overdue. Okay, so we're getting things that have a due date a long time ago, right? So less than this particular date, they're going to be stored in that table called overdue, or in that list called overdue, I should say. Here's something a bit more complicated. So we're joining multiple tables, with projecting some columns from those tables, and using compound conditions in the where clause. So we have the borrower table, the loan table, the book copy table, and the book title table. Right? And from that, we're selecting the borrower's forename, surname, the book title name, and the loan due date. The output doesn't have anything from this book copy table. Where we're using that book copy is in the where clause. Okay? So we're selecting those items from those four tables where the loan member ID is equal to the borrower member ID, and the loan copy ID is equal to the book copy ID, and the book copy ISBN is equal to the book title ISBN, and it's overdue. Okay, so essentially we're doing the same thing as we did in the previous query, but we're just getting the output into a nicer form than we had in the previous output. We can get even more complicated using nested subqueries. So sometimes what we want to do is to filter out things from a very large data set and basically put the expensive query, the thing that's going to be doing a lot of data manipulation, around the cheap filter query, which is going to just get rid of a lot of the input that we're just not interested in the first place. Okay, so here's our cheap one, which is basically where we're getting all of the overdue books, right? And then we're only worrying about those overdue books, so we can say we want to get, again, we're getting borrowers, book copies, book titles, and overdue books, where the overdue member ID is equal to the borrower member ID, and so on, as it was in the previous query. Okay, but essentially the first thing that's being done is just getting the books where they're overdue, really overdue in this case. Okay, so we're basically going to say, well, all of these books are basically write-offs because they're several years overdue. But I want to get, I'd also like to know who actually borrowed them. Maybe send them a letter to say that your borrowing rights have been suspended or something. Did you never return this book or whatever? So out of all the books in the library, the number which are that severely overdue are going to be very, very small, right? So the idea is that by doing this very simple query, which doesn't have, all it's doing is a filter on that particular value, we're paring the data down to a very small subset. And then this more complex query, we're only manipulating that small subset. So it can improve things quite substantially. Okay, so commonly what you can do is just get a single column table from your subquery. And you can treat it like a set, and you can use the inset membership predicate, right? So basically, here what we're doing, same query as before, getting the really overdue items. We're just getting the member ID, and we're getting the name and surname from borrower where the member ID is in this particular set. Okay, so again, we're doing a simple filter to get those ones with the really overdue thing, and then applying a slightly more complex thing on top of it. Okay, but in this case, it's a less complex thing, if that makes sense. Okay, so again, what we're doing is making things faster, better, quicker, because what we're doing is filtering our very large set of data down into something relatively small, and then linking the two tables after we've done the reduction. Okay, if we link together two really large tables, we're going to get one even larger table, and so there's a lot of data to manipulate, right? If instead we know that we're only going to use a really tiny subfraction of one of the tables, it makes sense to just start with that really tiny subfraction and then do the join together, because you'll end up with a lot less to work with. Okay, SQL also goes beyond relational data manipulation and allows you things like aggregate functions. So basically, it's summarizing data to give you statistics, or you can do computations of the sets that you've got to reduce to scalar values. The things that you get are actually very similar to the types of functions that you see in your Excel spreadsheets if you've ever used them. So we have count, sum, max, min, average, all those sorts of things. They're available to you as well in SQL. Okay. So if we want to know how many loans there are at the moment, we count how many rows there are in the loans table. Okay, so if the count wasn't there, if it was just select star from loan, it would return all the rows in the table. But by putting the keyword count there, it just returns a number. Right? Here, so select count distinct member ID from loan. So if it was just select distinct member ID from loan, it would give you all the unique names, member IDs, I should say, in the loans table, right? But with the count keyword in there, it tells you how many of them there are. So it's not how many books are out on loan, because some borrowers might have multiple books. It's how many of the library members have loans at the moment. Right, here's one that's more complicated. So let's look at the inner select first, right? So we're selecting all the things from loan where the copy ID is equal to the book copy, right? And TISBN equals CISBN. So the book title is equal to the book copy, right? And there exists a loan for it. And we're going to print out the book title name, right? So we're looking for all the loans at the moment, and for the things that exist there, we're printing out the titles. Yep. Okay. Group by is another useful thing that you can have in Excel, which basically splits your statistics up into groups. And similar to where we have a having, so it's the same sort of guard on it. So we do things like, we select all the book copies that are currently on loan. Easy. We select the member IDs what happens there?
We are using the loan table by selecting the member ID, and we just count the loans there, and we group them by the member ID.
Yeah, so essentially what we're doing here is it's almost like the distinct thing, except that rather than getting each person individually, it's grouping them individually, right? To count them individually. Right? So what's happening, so here is an example of the output that you would get from that query. Each line here has a unique member ID, and in this column here we have loans because we've explicitly said to store it as loans, right? So what had happened was in that original table there were 5 entries for member ID 101, 2, 2, 3, 4, and there were 4 for the next one, and 6 for the one after, right? So what it's doing is it's applying this count operator to the ones which have unique member IDs. Okay, so there were 5 instances of this member ID when we selected member ID from that table. And there were 4 instances of this member ID, and so on. So that's what's happened there. Okay, similarly here, this one has done the same thing, except that it's gone one step further, and it's saying group by the member IDs where the member ID has a count of greater than 3. Okay, so this table might be the output for this one or for that one, we don't know, because they're all greater than 3. It might just happen that all the borrowers had more than 3 books, or it might be this filtered version of it, where it's only looking at the ones who borrowed more than 3 books. Okay, so the point is, so SQL, yeah, it starts off with the relational work that is essential for manipulating databases, but then it provides a whole bunch of tools on top of it that can be very useful in manipulating data, right? And they do, at a certain level, map to the types of ones that you'll see in an Excel spreadsheet, where you can manipulate data using the functions in the Excel spreadsheet. Unsurprisingly, because Excel spreadsheets are also tables, right? And it is about manipulating data in the same way. So aggregate functions are really useful. It's one thing to extract data from your database, but if you're doing any sort of data management, you usually don't want to just look at the data, you want to manage your data and understand the patterns in your data and summarize the data that you have. You want to know not just who's borrowed what, but how many people have borrowed things, or how many people have overdue books, or what proportion of your users regularly have overdue books, that type of thing. You're doing higher level management than just manipulating the individual items within your thing. And all of these aggregate functions that go beyond the relational algebra, probably the reason why SQL has become the predominant database query language in the world. Right. So here's a query that finds the book that was borrowed first in the library. Okay. Why would you want to do that? Well, I don't know. Maybe if you were if it was the 100th anniversary of the library, you wanted to find the oldest book in your library. That would be one way of doing it, yeah? Or the number of times each book was issued in 2009. Now that one is perhaps more useful because you know then which are your most popular books, and you can order extra copies of the books that were most popular or something like that. Or you can make sure that you don't order extra copies of the ones which aren't getting borrowed, that type of thing. Right? So these types of queries are what makes SQL really powerful. Right? And it takes a long time to become an expert at this type of data manipulation in SQL. There is a very good reason why database administrators have had some of the top paying jobs in IT for decades now. Right? Because it is so important for businesses to be able to do this sort of thing, get this sort of information. I mean, this is a library, the example that we've been looking at. Imagine if it was a sales company and you were looking at sales patterns. Being able to recognize the patterns in your sales are very important. And yes, you could do it on a spreadsheet, but if you have very large volumes of sales, and we're talking about hundreds of thousands of items, then your spreadsheets are going to become unwieldy, and it's why you need to have the proper structured database behind it so that you can do optimization, so that that there is a compiler involved that will make your queries more efficient so that things can happen fast enough. So speaking of efficiency, one of the things we are interested in is query optimization. So the compiler itself can do some optimization, but the users, the people who write the queries, can also do optimization by framing the queries in different ways. And the type of things that you need to think about are things like how many rows are there to find. Okay, so if you can minimize the number of rows that you're going to be searching through, then that's going to make things faster. How difficult is it going to be to find them? So the more joins you have to do, the slower things are going to happen as well, because you're putting together tables, and as soon as you start putting things together, that takes time to do the joins and more memory to do the extra things, that sort of thing. And where do we store some intermediate results? So how much space are we going to be using as we do those intermediate steps? If we can minimize the size of that space, then it's going to be more efficient as well. So possible approaches include structuring the queries, so the S in the original SQL, which standard for structured query language. Filter large data sets first before joining. Okay, so if you're joining two tables together and you're only going to be using a small amount of data from that second table, filter that second table before you join it with the first. Right? And again, project columns before joining. Remember, project is the idea of just selecting the columns that you're going to use from a particular table. If you've got a table with 10 columns in it and you only need to use 2 of them, get rid of those other 8. They take up memory. Right? database management systems, the commercial versions at least, use automatic query optimization. Even the non-commercial versions like MySQL do it to a certain level, but certainly things like Oracle do it extensively. That includes reorganizing the order in which parts of a query are executed. So we talked about ways that you can change things around so that you're working with smaller data sets and that sort of thing. The commercial ones will try to do it automatically, right? The database management systems need to know what queries are going to be asked in order to do that efficiently, right? So they need to have some understanding of the structure of the queries that are going to go into it and the tables that are going to be used and that sort of thing. Now, it's all very well to say that the database management systems will do optimization for you. Sometimes they can be more efficient than a person. Right? But I think if you had an experienced database management operator and the best database management system, the human operator could probably optimize things better than the compiler could, just because they have a better intuitive understanding of the tables and the way that the data is handled and that sort of thing. For incredibly large data sets, you know, we're talking big data type data, maybe that's no longer true. I haven't got a lot of experience of working with big data myself, but the way that big data is stored is not in traditional database management systems anyway. It's a whole new ball game, right? So you will still see query languages like SQL being used for them, but the underlying data structures that are being used are different because of the way that big data and cloud services work. Right? So it changes things quite significantly. For a standard business operation though, where you're not talking about millions of pieces of data or hundreds of millions of pieces of data, you might still be talking about millions in the case of, say, Boots or Sainsbury's or something like that. They're still using traditional databases. Okay, so in terms of the access to data, scanning through data files is very expensive, right? Disk access is much slower than memory access. Okay, so you're talking orders of magnitude. Even if you're talking about solid-state devices, there's still at least an order of magnitude slower than your dynamic memory on your computer, right? And when we're talking about databases, we're probably not talking about solid-state devices because they don't have the magnitude volume as a traditional storage device, like a hard disk. Right? And hard disks are at least 2 orders of magnitude and sometimes more slow than dynamic memory. Right? So you want to minimize the amount of time that you spend reading data from disk. Okay. If we use fixed length records in flat files, we can devise special representations of these that can read block by block, not having to scan and work out where the end of a row is and that sort of thing. It's much quicker and faster to preload things like that. So that's something that we want to do. If we have an index to the row position in a large file that's stored like that, of fixed length things, we can get much more quickly to the row by its index. because we have that direct reference to exactly where it is on disk, because it is just a multiple of these fixed size blocks since the start of the disk. It's very easy to find it on disk. It's still slow, but it's not as slow as searching for the start of a record where all the records are different lengths. Okay, and then we're talking about very large data sets. So I'm still not talking about big data, just things like a very large company like Boots or Sainsbury's or that sort of thing, where you've got hundreds of different branches around the country, each of them are in many cases doing thousands and thousands of transactions per day. You're getting very large data sets. And so you're not going to fit, in many cases, a single table on a single storage device. Okay, so imagine that you were keeping track of all the sales for Sainsbury's, even in just one large store, right? You wouldn't be able to keep track of every single purchase in that store in probably even a day, let alone a week, in a single table on a single storage device, even if you had a terabyte of storage. Okay? But at the same time, we might be looking at queries that are only accessing a few rows. Like if we want to look at the sales of a particular product amongst all the sales that have gone on for a week in a store, that product might be a really low volume product. You might have only had maybe 100 sales out of the hundreds of thousands of sales that you had during the week. And so rather than just having a linear thing, what tends to happen is typically the data gets divided into what's known as a B tree. And the B tree is a graph that basically halves the search space each time. B tree stands for a binary tree or a special type of binary tree. And when you're searching for things, you, right from the very first step, split the memory into two parts, and you know that it's in one part or the other part. And then you go to your next decision point, and again you split it in half. So each time you're searching through the tree, you're reducing the search space by a half, rather than linearly searching through all of the data that you have. Okay, so I'm not going to go into the details of how you do B trees, because typically that would be in the second year advanced algorithms module, and I don't think you lot have had enough programming experience to appreciate the mechanics of it. But just to understand this idea that linear search through a list of records can be really, really slow, right? If we have this idea of at least being able to split the search space in half each time, it massively speeds things up. Okay, so even though conceptually our database might be stored as a linear list of records, in practice we use more efficient data structures, is the idea. Okay, so finally, just briefly touching on the technicalities of it. Okay, so in terms of which database you will use while you're studying here, we would say use MySQL, okay, because it's a free and well-established version of SQL. It's been around for literally decades now. It runs under Windows, Unix, and Linux, and Mac OS. I don't know why I put it on the list. It's a form of Unix anyway, right? Uses the standard SQL query language, and there is extensive online support for it in terms of tutorials and discussion groups and that sort of thing. It's just, you know, there's so many people around the world that have used it and have used it for a long time. This applies for you next semester, so don't worry about it now, but basically we have MySQL installed on the departmental servers, so you don't need to worry about installing it yourself. You can if you want to play around with it, but is big, right? So when you come to use it, you'll use our installation of it, right? In terms of how you use it, you're going to be using Java to connect to it, right? The Java Database Connectivity, or JDBC API, allows Java to communicate with, well, virtually any tabular data, including relational databases, various different forms of SQL, but also flat CSV files and that sort of thing. So if you export something from Excel, for example, it can use that data. It supports basically all of the different types of transactions that you would expect, to insert data, to query data, to update data, and to roll back transactions. So a rollback is where you do something to the database and you've decided that that was the wrong thing to do, so it can go back to the previous state. Okay, so the key components of the Java package containing all the JDBC classes and the driver to drive the MySQL database. So you will connect to the department's MySQL server and you will have your own database on it when you do your assignment. Okay, you need the MySQL driver. You get the particular version of this driver for Java and install it in your class path. Right? So that's for you if you want to run it on your local laptop or whatever. If you're going to be using it on the departmental machines, it's all there for you already. Right? But for those of you who want to do your own independent work, you're going to need to do that. And then you go through the process of connecting with a database, right? Basically, go to your server, connect with the username and password that you set up when you created your MySQL account. And you do whatever you need to do with it. At the very end, you need to make sure you close your connection. Okay, so you always close your connection to the database. If you want to execute a query, here's the key bit. Right, so this line here is effectively your query. So what I'm describing here is basically Java wrappers that go around the SQL that we've been talking about today. It looks probably a lot more complicated than most of the Java that you've looked at so far this semester. You don't need to worry about it. It is just templates. Okay? So you will cut and paste this code next semester. Okay? Here, in the ... this is where you actually write your own code, right? So this is where you've got this data that you've got out of your database. Let's do something with it. Okay, here's another example where we want to change some of the data in the database. So again, this is the SQL bit. We're updating the table lecturer, setting the office to 153 where the name is Emma Norling. Right? So presumably I moved offices and we're changing the room number. Okay, so again, just a summary of some of the commands that you'll use. Create table, drop table. Drop table means to basically delete the table, right? Insert put stuff into the table. Delete, so delete rows from your table. Updating the database, so getting stuff from the table, selecting stuff from the table, updating again. So these last few slides, I'm putting them up so you know what's going to come. You don't need to take it all in now. It's going to be much easier when you actually do it in practice. Okay, so in summary, we've got these relations between data, okay? And you don't really need to worry about the technical terms that are being used there, but essentially we have this relational algebra, which is procedural, which is the thing that manipulates the data in the database, right? SQL basically is an impure implementation, a messy implementation of relational algebra that drove the original author of relational algebra crazy, but has turned out to be so powerful that it's become the de facto standard for database manipulation in the world. Right? In particular, the aggregate functions that are provided by SQL are very useful in practice and are the thing that a lot of businesses really want in terms of their database management. Dealing with large amounts of data is difficult. It uses a lot of memory and it takes a lot of time. We want to optimize our queries as much as possible. We can write queries in different ways that does optimization, but also the computer can reorganize queries to make them more efficient and can store the data in ways other than the conceptual linear list of data that we have in our heads. Okay, so it's fine to think of the database as a list of items, but in practice it's not stored that way. JDBC is the toolkit that we're going to be using for connecting Java to databases. We're going to connect it to a MySQL database, but it will connect to any type of SQL database and other types as well. There are no discussion questions this week. There are problems for you to look at in your own time. And those of you who've accessed the slides in advance will realise that I actually put these up yesterday. So here is a table, and I want to know, this first question is about the relational algebra. So I want a relational algebra expression that yields a table containing orders with their corresponding cities and quantities. And I want to know what's the result of that expression when you apply it to this table. So there's two parts to the answer here. The next one is an expression to yield a table of products and quantities with greater than 100 of each product in the result. I only want the expression in this case, don't worry about what the table would look like. Define a table country linking each city to a country in the set France and UK. And then write a relational algebra expression identifying the country for each sales order. So what I want here is this table, country, and the expression that you would use. So the table I want is the country table, not the result table. Right? Okay, second problem. This time we're talking about SQL. Right? So we have a relational schema where so what this is saying is we've got 4 tables where the columns are the comma separated list things in there. And I want SQL queries for each of these things. So first of all, the name of the employee who earns the highest salary. The names and addresses of all employees who live outside the city in which they work. The name of the company with the most employees. the names of all employees who earn more than the lowest paid manager, right? And give the names of all employees who earn more than the lowest paid manager in the company at which they work. Okay, so these are complicated, right? It is going to take some figuring out. So, expect to spend some time here, right? There's definitely more work in these second set of problems, the SQL problems, than there are in the relational algebra ones. You will need to spend quite a bit of time thinking about what those queries would look like.